Bismillah, alhamdulillah, wa salatu wa salam ala rasulillah. This is a second example for applying the Laplace transform to do circuit analysis. And this is assessment problem 13.5 in Nilsson. So it's an assessment problem in Nilsson, the textbook that we are using. And it says the DC current and voltage sources are applied simultaneously to the circuit shown. No energy is stored in the circuit at the instant of application. Now it says already that there is no energy is stored in the circuit, but it shows at the time some switches. So for that reason, I want to double check by checking if that's correct for t less than 0. So it's for t less than 0. My circuit looks like this. I have the current source. This is 5 ampere. And this was closed. This switch was closed, so it is now a short circuit. And then I have this capacitor, and I'm assuming that it has been closed for a long time, or the circuit has been like that for a long time. So this is now an open circuit, and this inductor will be a short circuit, and I will have a resistor in here of 3 ohm, and then I have another resistor in here, and then the rest of the circuit will be open because this other switch was open during that period. Now as you can see, now this current is all flowing in here, so there is no current flowing in this branch or in this branch, and the voltage source is disconnected, so the circuit has no power, and therefore the initial voltage and current through the inductor and the across the capacitor are all equal to 0. Now for t more than 0, this situation will change because this is now open. So I will have a circuit. My circuit now will look like this. Let me, and just excuse me for writing this in here because it's easier. So now for t more than 0, I have the current source, but I want to take this to the Laplace transform, and this is a constant 5 ampere, which for t more than 0, which is exactly the same as saying it's 5 u of t ampere. So the Laplace transform of this becomes 5 over s, and this switch now is open, and then I have the capacitor, and for the capacitor it should be 1 over sc, but c is equal to 1, so this is 1 over s. So just a reminder that the capacitor impedance is 1 over sc. And then for the inductor it should be ls, but l is equal to, it should be ls, but l in this case is equal to 1, so this is going to be just s, and these values are in ohms. This is in ampere. And then I have 3 ohm in here and 15 ohm above there. And for the voltage source, I have to take the Laplace transform of 15 u of t, which is 15 over s, and the unit for that is V. So this is now my circuit. What's required is to find, in part A it says derive the S domain expressions for V1 and V2. So V1 is here across the capacitor, and V2 is the voltage from here to here. For the analysis I will use the node voltage method because the easiest in this case. I have only 2 nodes, and the voltages will be on the nodes v1 and v2. And now I need to write the equations, so I have minus 5 over s plus v1 over 1 over s, that's s times v1, and then plus I have v1 minus v2 over s, and these are equal to 0. The sum of these is equal to 0. Now I'll just multiply both sides by s, and I will take this to the other side, so the result will be s square v1 plus v1 minus v2 is equal to 5s. And then combining similar terms together, I will write this in a different color, let's say blue. So I have s square plus v1 plus 1 multiplied by v1 minus v2 is equal to 5s. And this is my equation number 1. Now for the second equation, very similarly, I will have v2 minus v1 over s plus v2 over 3 plus v2 minus 15 over s over 15. And this is equal to 0. And to simplify and get rid of all the fractions, I'll multiply both sides by 15s. Now this is s, not 5. Now doing so, I will have 15s over s is 15, so that's 15 v2 minus 15 v1, and then plus 15s over 3 is 5s, so I have plus 5s v2, and then when I multiply 15 will cancel, and what will remain is s, so I have then plus s v2 minus 15 is equal to 0. And it is minus 15 because the s cancelled. And then by collecting similar terms, I have v1 appears only here, so I have minus 15 v1 and for v2 it appeared here, here and here, so I have 3 terms, so that's plus, that's 6s plus 15 v2, and on the other side I have the 15, and this is equation number 2. Now to solve this system of equation to get expressions for v1 and v2, I will use the Kramer's rule, and for that I need to calculate the determinant of s square plus 1 minus 1 minus 15 and 6s plus 15, and this comes from these coefficients over here in the 2 equations. And clearly if you multiply these 2 together now, I will definitely have s cube as the highest power. The factor of the s cube is 6 because it can come only from s squared times 6s, and then the factor of s square is 15, and the factor of s is 6, and then plus 1, plus 15, sorry, because that's 15 times 1. And then I have minus 1 times minus 15, so that's plus 15, or minus 15. So minus 15 plus 15 is 0. And well, I know that I have to divide by this later, and to do the Laplace transform I know the highest power of s, or the coefficients of the highest power of s should be 1, so I will just take 6 as a common factor. So what remains is, and s is repeated in all of these, so I will get 6s as a common factor, and then I will have here 6 square plus 15 over 6, so that's, I'll just write this in here, 15 over 6 is simply 5 over 2, which is 2.5. So 2.5 s, and when I take 6, divide this by 6s, I will get 1. And I can factor this because this is simply, well, s times s. Now the sign of the constant factor, constant term is equal to 1, is plus, so the two signs are similar. And then I need two numbers whose multiplication is equal to 1 and addition equal to 2.5, and these two are simply 0.5 and 2. So this is my delta. Similarly, you can find the delta 1, which is the same determinant, but I have to replace the first column by 5, and there is no s in here because when you multiply by s, the s will disappear. So the coefficients, the terms are 5 and 15. And the second column will stay as it is. And you can calculate this to get something that looks like this: 30 times s plus 3. For delta 2, well, the first column of delta is going to be the same, so this is s square plus 1 and minus 15. And for the second column, I will replace by 5 and 15. And if you calculate the determinant of this, you will get 15 s square plus 6. Calculating these determinants, you can find V1, which is simply delta 1 over delta. Delta 1 is 30 s plus 3, and in the numerator, let me write the numerator first. The numerator is just 6s s plus 0.5 s plus 2. In the numerator, I'm going to have 30 s plus 3. Now 30 over 6 is 5, so I'm just going to delete this and write 5 in here. And then for V2, in the numerator, we get the same numerator, s plus 0.5, and s plus 2. And this is my numerator, so that's, oh, I have 6 in here. And then 15 s squared plus 6. Now 15 over 6 is 2.5, so I'm just going to write 2.5 in here. And these two, of course, are in volts. And these are V1 and V2 in Laplace domain, or in frequency domain. Now, in the second part, it's asking that I find V1 and V2 in time domain. That's part B. And to do this, I need to find the inverse Laplace transform. So V1, which is equal to this, I'm just going to copy this. Copy and then paste in here. This is going to be equal to A over S plus B over S plus 0.5 plus C over S plus 0.2. So now to find A, B, and C, you need to use the cover-up method. And for the first one, I will cover the S. So I multiply both sides by S to get A, and I will substitute for S equal to 0. And when doing the substitution, this is 15 over 2 times 0.5, which is equal to 1, which is just equal to 15. Similarly, you can calculate B and C. In this case, you will find that B is equal to minus 50 over 3 and C equal to 5 over 3. Now calculating the inverse Laplace transform, you will get V1 of t, which is nothing but 15 minus 50 over 3 e to the minus 0.5t, and then plus 5 over 3 e to the minus 2t, and this is multiplied by u of t, and of course the unit is in volts. Similarly, you can calculate V2 of t is equal to 15 minus 125 over 6 e to the minus 0.5t plus 25 over 3 e to the minus 2t u of t volts. And this is my answer for part B. Now for part C, it asking about V1 0 plus and V2 0 plus. Now what you need to understand in here is that these two expressions are for t more than 0. So to find V0 plus and V1 plus and V2 plus, all what you have to do is to substitute with t equal to 0 in this case. So V1 0 plus is simply 15, and then u of 0 is 1, so I don't have to worry about the u of t at the end. and this is simply 50 over 3 plus 5 over 3. Now if you want to have a common denominator, this will be 45 over 3. So this is in fact equal to 0 volts. So that's 15 minus 50 over 3 plus 5 over 3, and these two has common denominators already. This is 15 over 3 is 45 over 3 is 15, that's correct, and minus 50 plus 5 is minus 45 plus 45, that's 0, so that's correct. Similarly, V2 of 0 plus is equal to, this time I have a 6 in here, so I need 90. So this is 90 over 6. And 90 over 6 is equal to 15. This is minus 125 over 6 plus 50 over 6. Okay. So 90 plus 50 is 140, so this is 140 minus 125 over 6, and this is 15 over 6, which is equal to 2.5 volts. Finally, in part D, you want to calculate the steady state values. The steady state values are simply the values of the voltages at infinity. So this is taking the limit, of course, and as you can see that if you take the limit, this will go to 0 and this will go to 0 because it has a negative power in there, and then what's left is 15. And for V2 it's the same thing, so V1 is equal to V2 and they are at infinity and they both converge to 15 volts. And this concludes my video. Thanks for watching. Subhanakallahumma bihamdik, ashhadu an la ilaha illa ant, astaghfiruka wa atubu ilayk.